Hello. In this video, we're going to continue our study of infinite sequences and series by looking at a particular type of sequence and a particular related type of series, and we'll explore when the sequence converges or diverges and when the series converges or diverges. And I want to start us all off with just a silly-ish, but hopefully a motivating example. Let's suppose I have a very odd, strange bug, and from its starting point, let's say right here, it takes a step forward of size 1 inch. Let's say it lands right there. I'm just going to say that length right there, that's 1 inch. Why the heck not? Now, let's say that this bug is so strange that after taking that step of 1 inch, it stops and it waits for a sec, and then it takes a step forward of 1/3 the size. So bear with me on the scale here. Hopefully that's about 1/3 of an inch based on what the first step was. And then it stops and it waits. And then on the next step, it goes forward 1/9 of an inch, 1/3 of the length that it just went. And let's say that it continues to do this in such a way that every time it pauses and then takes its next step, it goes forward 1/3 of the length that it just went on the previous step. So eventually it's taking very, very, very small steps indeed. We're going to answer two questions in the course of this video and generalize from what we observe in this example to make some more general statements of fact. But the first thing we're going to address is, what is the sequence happening here? If I let dn be the distance that the bug moves in step n, in other words, making n equals 1 the first step, n equals 2 the second step, n equals 3 the third step, and so on, then what is the sequence of those step sizes? Well, notice that the first step is size 1, the next step is size 1/3, and then it's a size 1/9. I keep multiplying by 1/3 each time to get from one step size to the next. And that's what I'm indicating here with these blue notations that I just added. Each step is 1/3 of the size of the step that came right before it. And that's exactly what I'm describing in these arrows and these times 1/3 that are happening there. So because the first step was size 1, what I'm getting is a sequence where the nth step is 1 times 1/3 a whole bunch of times. How many times do I multiply by 1/3? Well, in the first step, when n is 1, I didn't third anything yet. I didn't cut the step size down by a factor of 3 yet. In the second step, when n is 2, that's the first time I cut it down by 1/3. And when n is 3 for the third step, that means I've cut it down by a factor of 3 twice. When n is 4, I've cut it down by a factor of 3 times. And so I keep seeing this difference of 1 where the step size minus 1 tells me how many thirds I've multiplied by. And that's exactly what I'm writing down here in this boxed area. That n minus 1 comes from the fact that I've multiplied by 1/3 one fewer times than the step number that I'm at. Because the first time I take a step, I haven't cut it in thirds at all. And so another way of saying this is I just have, well, 1 times 1/3 to them. I don't really need that times 1 in the front, so I could write it as 1/3 to the n minus 1. Or even if you really wanted to, 1 to the something is 1 in the numerator, so I could also write this as 1 over the quantity 3 to the n minus 1. That would be perfectly acceptable too. And over the course of this video, now that we've addressed the first question, we'll kind of come back over time and address the second question about how far it's going to travel, but maybe keep that on the side of your mind for now. So here's what we've discovered. The bug's step sizes follow this sequence, 1/3 to the power n minus 1. And you can see my little notation here to write a sequence. I'm just reminding the reader, you, that I have a sequence. I'm calling it d for distance, the step size. Its index is n, so when I see that n down there, that's the n that's happening in the formula for the sequence. And this stuff on the right is telling me that a sequence starts at n equals 1, and then it increases to 2 and 3 and 4 and so on, and it just doesn't stop. It's an infinite sequence. So all this notation is just a reminder of everything that we set up on the previous slide. So in other words, I could say this sequence dn looks like 1, and then 1/3, and then 1/9, then a 27th, and so on. 1 over the powers of 3. And the first term really does fit the same pattern because 1 over 1, 1 is 3 to the 0. That's also a power of 3. And so the key feature that I pointed out in the previous slide, and really where this sequence came from, is that each time to get from one term to the next, I keep multiplying by 1/3. That's what I've written in green up there. Each time I multiply by 1/3 to get the next term. That is precisely what I'm describing in the definition box down below. A geometric sequence is one in which each term is equal to the previous one times multiplied by a specific fixed value. And it's very common to use r for that value. So in our example up above, the first term was a 1. I'm noting in the definition box here that it's pretty common to use a to mean that, the first term. And r is a third. That's the number that I multiply by each time to get the next term. And you can think of that r as coming from r for ratio, in the sense that the ratio between successive terms is always a factor of 1/3. And that's never changing. Here are some other examples of geometric sequences down at the bottom. For each of them, I've provided the a, the starting value, and the r, the 1/2, the ratio, the multiplicative value, just so you can see them and better understand this definition. But in the future, I hope you would be able to quickly and relatively easily go from, for example, given a equals 4 and r equals 1/2, you should be able to write out a whole bunch of terms of that sequence pretty quickly, remembering that that means the first term is 4, and then each time to get to the next one, I keep multiplying by a half. So 4 cuts in half to 2, and then 1, and then a half, and then I get 1 over powers of 2, and so on and so on and so on. Or vice versa, if I gave you these terms of the sequence, and I said, do you see the pattern here? I'm trusting that you would notice that it starts with a 4, and each time it cuts in half. It's divided by 2, it's multiplied by 1/2, and you should be able to see that it's a geometric sequence with a equals 4 and r equals 1/2. In other words, you should be able to go back and forth between these two pieces of information, but just for your learning right now, I'm giving you all of the information to see everything at once. In example 2 down here in the bottom left, I'm showing you that yes, it is totally possible, and we'll have an example coming up pretty soon, for r to be negative. That is perfectly fine. All that means is that when I multiply by r, that multiplicative value, then the sign of the terms will keep switching. So in this example, a is 1, so I start with a 1, and then each time I multiply by negative 1/3 to generate the next term, and so I get negative something, a third, and then when I multiply negative 1/3 again, I have two negatives making a positive, and then I multiply again and I have a negative, and it's just going to keep alternating in sign. So when I have a negative r like that, that's totally reasonable. It's just going to cause the sequence to alternate plus minus, and so on. Here are a couple other examples over here on the right. In the third one, a is 2/3 and r is negative 2/3, so this is also going to oscillate in sign, plus minus, and you can also see how the numerators are powers of 2 from the 2, and the bottom is powers of 3 from the 3 in the r. And then just to give you a slightly different example in number 4, I picked a quote-unquote relatively large r value. I picked 6. It doesn't seem like a big number, but it's big in the sense of what we're going to talk about in the next slide, which I'll get to in a second. But it's bigger than 1, essentially. So what that's going to do is it's going to cause the terms of the sequence to grow in value. So even if I start with something relatively quote-unquote small, like a quarter, when I multiply it by 6, it becomes a lot bigger. I get 6/4 or 3/2 there. And then when I multiply by 6 again, I get 18/2 or 9. And then when I multiply by 6 again, it just gets bigger and bigger and bigger, and it's going to keep growing and growing. And this sequence is going to diverge to positive infinity because the values keep growing. You can kind of see why that's happening. I'm multiplying by a number bigger than 1, so the value of the terms keeps growing and growing. And that's pretty much what we're going to get into in this statement of a bunch of facts right here. When I have a geometric sequence, given two things about it, let's say the first term is a, and its ratio, its multiplicative, common multiplicative term to generate the next term from each one before it, let's say that multiplicative ratio is r, then if I only know those two things, then it turns out I can tell you whether the sequence is going to converge or diverge. And in fact, it doesn't even depend on A. I don't really need to know A. All I need to know is the ratio R. Because you can see I have if something, if something, if something, and then all the conclusions come out. But none of them really depend on A. You can see some A later, but that's going to tell me about what the sequence may or may not converge to. But whether or not it does converge is all based on R. And that's what I'm trying to get at in the title of the slide. So let's look back at some of these examples on the previous slide. My bug example of 1, a third, a ninth, a 27th. I hope you can see after thinking for a minute that that's going to converge to 0. I keep getting 1 divided by larger and larger and larger values in the denominator. It's getting tripled each time. So those values are going to decrease down to 0. That's precisely the situation I'm describing in bullet point 1 in this theorem. If I have an R that's less than 1 in magnitude, it's smaller than 1, and I'm thinking of the positive 1/3 that we have for now. We'll think about a negative 1 in a second. But if I have a small r that's less than 1, then the sequence will converge to 0. And specifically, as I note here, if that number was positive, the sequence, when I say it, I mean the sequence, is going to decrease to 0, even more specifically than just going to 0. When I say it down here, I mean the sequence. And that's exactly what happened in the 1, a third, a ninth, a 27th, and so on. It's not just that the terms are going to 0, they're going down to 0, they're decreasing. Look at, for example, bullet point number 2 down on the bottom left here. That's effectively the same sequence, but I introduced the alternating plus minus by making r negative 1/3 instead of positive 1/3. But look at those terms. They're the same numbers. 1, a third, or negative a third, a ninth, or negative a ninth, a 27th, or negative a 27th. They're the same numbers, they just have alternating signs. And so these values, these magnitudes, are still going to go to 0, except instead of decreasing, so like let me draw it down here, if r is positive, the values go down to 0 like this. If r is negative, then they go to 0 by getting closer but alternating back and forth. So I have positive 1, negative a third, positive a ninth, negative 1/27. And in magnitude, they're behaving just like this one back here, but the signs make them kind of oscillate and alternate towards 0. So that covers all of the situations where r, the ratio, is less than 1 in magnitude, in absolute value, if it's between negative 1 and positive 1. Now, if r is exactly 1, then what's the sequence? It starts at a, I multiply by 1 to get the next term, and I get a. And then I multiply by 1 to get the next term, and I get a. And this is just a boring, but I guess in that sense also kind of quite interesting sequence in that it's constant. It never changes. Its terms are always just constantly a. So obviously that's going to converge to a. It gets closer and closer to a because it's already always at a. I hope you see what I mean by it's kind of both boring and interesting all at once. What would be different if r were negative 1 exactly? Well, that's only slightly less boring than the previous one. It's going to alternate in sign. If I start at a, then I multiply by negative 1 to get the next term, that's going to flip the sign. And then it's going to flip again, it's going to flip again. And so this is going to make the sequence diverge because it's kind of oscillating back and forth. It's at positive a and then negative a, and then positive a and back and forth and back and forth. What if r is bigger than 1? This is exactly what I was hinting at with the example number 4 down here in the bottom right. I said I picked a quote-unquote big number. R is 6. It doesn't matter that it's a big whole number. What matters is that it's bigger than 1. And that's going to cause the terms of the sequence to get bigger and bigger. If I start with something, it doesn't matter what it is, and I keep multiplying by r to get the next term, this is what I'm writing out here, then if r is bigger than 1, that multiplier here, r squared, r to the third, r to the fourth, and so on, those are all going to grow and grow and grow to positive infinity. Think of something like r equals 6, or r equals 10, or even r equals 1.0001. It's going to grow to infinity, a little bit more slowly than if r had been 6 or 10 or a million, but it will continue to grow. And somewhat relatedly, if r is a number in value that's bigger than 1, but it's a negative sign, so these two are very closely linked. If r is less than -1, then I get the same thing kind of happening. The terms are growing in value, but it's oscillating in sign. So if I think of it as an example, like for number 4, my terms would be growing like this in value. Then in number 5, I'm seeing something like this, where it's like here, and then it's a bigger negative, then it's an even bigger positive, and then it's an even bigger negative. It's going to keep getting wider and wider away. And that's what I mean by oscillating to plus and minus infinity kind of all at once. So now it turns out we kind of know everything we need to know about a geometric sequence. If you know what A and R are, either you're given them or you were given the sequence and you ascertained the pattern, then just by looking at R alone, you can conclude confidently whether the sequence converges or not. So let's go back to the follow-up question I asked at the beginning of the video about a geometric series. What is going to happen if the bug keeps walking and following those steps of size 1, a third, a ninth, a 27th? So we can interpret the conclusion of this geometric sequence theorem as saying the bug is taking steps whose sizes are getting smaller and smaller and smaller and shrinking to 0. So that's why on the first page here, I drew these steps getting smaller and smaller and so on, so that you couldn't really tell. I don't want to say going to 0 to confuse you about distance, but the size of the steps is getting smaller and smaller. And essentially, if I wait a long enough time, I won't really be able to see that the bug is moving, because it takes a step that's such a small fraction of an inch. But that follow-up question was, how far will the bug walk if I'm allowed to let it take infinitely many steps? And that might seem kind of like a big physical stretch of the imagination, but in some sense, honestly, so what? That's kind of what math is all about, stretching our imagination and trying to conceptualize things that we can't literally conceptualize. But another way to think of that is if the bug makes these step sizes, they're getting smaller and smaller, then it's taking much less and less time to actually do them. And so, theoretically, when you walk across the room, you're taking infinitely many steps. They're just infinitesimally small, so you don't really notice. So maybe that will quell your philosophical qualms temporarily. But really, this is all just a coded way of asking this question. What is going on with this geometric infinite series, this sum of the terms of a geometric sequence? Instead of listing them like this, what if I say, let's add them together? 1 plus a third plus a ninth plus a 27th. So this is another way of saying, if I do that jump of size 1 inch, and then a third of an inch, and then a ninth of an inch, and then a 27th, and so on, this is a way of asking, what's that entire length? If I keep doing that forever and I end up moving towards a particular location, what is that total distance traveled? So let's say that total distance traveled is s. I'm going to use s for sum because we're adding together a bunch of terms. And so I'm asking the question, what is the value of s if it's equal to 1 plus a third plus a ninth plus a 27th plus blah, 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 blah. So I'm going to do some steps on here that I expect you to follow along with the logic of what I'm doing. I'm not saying at all that you should come up with what I'm doing as a method for solving a problem. I'm demonstrating it for you this once, and then on the next couple of slides, we'll make some general observations and statements about what I did in this example. But this is not a method that I'm expecting you to invent or really even employ. We're going to use it to state a general fact, a theorem coming up. So what I'm going to do right now, this is kind of the tricky step. I'm going to take both sides of this equation and multiply through entirely by, let's see. I'm going to pick 1/3 to multiply through both sides of the equation by. So on the left, kind of nothing to do. S becomes a third of s, nothing to do. But on the right side, I have to distribute that 1/3 into all of the terms. And maybe as I write this out, you'll start to see why I picked 1/3 there. It's not a coincidence that that is r, the multiplicative ratio of the geometric sequence that we're talking about all along. That's why I'm choosing that 1/3 here. Because what happens? When I distribute the 1/3 into the 1, that becomes the 1/3 term that I'm going to write down there. And then when I multiply and distribute into the 1/3, I get 1/9. When I distribute that into the 1/9, I get 1/27th, and this is intriguing. Do you see what's happening here? I get exactly the same infinite sum, the same geometric series, except it's missing that first term, the 1. Everything else they have in common. The 1/3, the 1/9, the 1/27th, the 1/81th, or whatever the heck you want to say that. Everything else they're going to share, but it's that 1 in the front that they differ by. So what I'm about to do, and I'm going to open a new page on the next slide here to continue, is I'm going to subtract the second line down here from the first line. I'm going to take the whole second row and subtract it away from the top row. The reason I'm doing that is all of these terms are going to cancel out, and I'm going to be left with the just the 1 in the top line after I subtract everything else. And there's all the magic happening. I'm doing that top row, and I'm subtracting away the second row. All of the 1/3, 1/9, 1/27th, and all the later terms, they cancel each other out. I have just the 1 left in the top row that doesn't cancel out anything down here. And then on the left, I have S, one of them, minus 1/3 of them, so I'm left with 2/3 of them. And so, just by multiplying across by 3 and dividing by 2, that allows me to conclude that the sum is 3/2. And that's it. The sum of this geometric series is 3/2. And remember that we discussed in some prior videos, the notion of a series adding up to something, the series converging to a particular sum, means that as I add more and more and more terms from the series, then the partial sums, the running totals, keeping track of the total sum as I add a bunch of the terms together, that those partial sums, the running totals, will approach that sum value, the 3/2. They'll get closer and closer and closer. So I've just pulled up a handy little calculator app over here. I did the first 2 terms. This is the quote-unquote the second partial sum. You can see I added 1 plus 1/3, and I got, quite obviously, 1 1/3. So what if I add the next term, 1/9? I get 1.4. And what if I add the next term, 1/27? I get this. And I keep tacking on the next term in the geometric sequence, the next term. I keep tacking it on to the previous running total, the previous partial sum. So you can see I'm using the stored information from the calculator, that 1.481. That was the total of the first 4 terms, and now I'm tacking on the 5th term, the 1/81. And then let's add on the next term, 1/243. And then let's add on the next term, 1/243 times 3 is 729. And then I kind of run out of my ability to do division by 3 and multiplication by 3. But see what's happening at 1.4, 1.48, 1.49, 1.499. Seems to be getting eerily close to 1.5, right? Well, 1.5 is 3/2. That's the summation, the sum of this series that we're expecting. All right, cool. So what I have stated in here in the theorem box, and what you, my students, can follow along with on the notes that I have given you on our course website, is a way to kind of adapt what I just did in that example with the specific numbers a equals 1 and r equals 1/3. On my notes, I guide you into doing essentially what we just did in this last problem, multiplying through by r and subtracting the 2 equations to solve for something. You will discover this more general fact, and if you do some Googling around or searching on YouTube, you'll find all sorts of other videos. That's why I've chosen not to replicate the whole process here, and I just applied it to our one example. But here's the conclusion you'll get. If you take a geometric series whose first term is a, and whose multiplicative ratio is r, just like we've been considering all along, then if r is between -1 and 1, then the series converges. And not only that, we can tell you what it converges to. And so there I've written out the same information just slightly differently. I'm saying that this infinite sum, this infinite series, where the first term, when I plug in n equals 0, r to the 0 would be 1, so the first term will be just a times 1, or just a. And then the next term will be a times r to the first, and then a times r squared, and a times r cubed. This is exactly that geometric series with the first term a and multiplicative value r, written in summation notation. Then all of that adds up to a over 1 minus r. And just a quick side note, in the grand scheme of things, as we go through our study of infinite series for the next couple of weeks, take note that this is a really beneficial and useful theorem because we actually get the sum of the series, the value of what all the terms add up to. Moving forward, that's going to be pretty darn rare, unfortunately. Most of the time, we're going to have to be content with saying whether or not a series converges at all, and kind of leaving it at that. And only very rarely will we be able to say what the series adds up to. When it's a geometric series, we know exactly what the sum is. And that's, in fact, a beautiful, useful thing. It's maybe hard to appreciate now, so kind of have that on the back of your mind, too. And then, as it turns out, if r is anything else, if it's outside of the -1 to 1 range, so in other words, if it's less than or equal to -1, or if it's bigger than or equal to +1, then the series diverges. So here's me applying the first part of this theorem that says when r is between -1 and 1, like we had in our example with the bug where r was a third and the starting term a was 1, then the sum of that series should exist because it's convergent, and I get the sum of the series to be 1, which is a, over 1 minus a third, which is, and that evaluates to 1 over, let's see, 1 minus a third is 2/3. 1 over 2/3, reciprocal is 3/2. There's the same sum value we got already. And in fact, that division, 1 over 2/3, is pretty much what we did to solve for s in this last step, to divide both sides by 2/3, or to multiply by its reciprocal, 3/2. Let me show you another example of the second part of the theorem. Let's take as an example here, let's say like 1 minus 2 plus 4 minus 8 plus 16 minus 32, and so on. Look at that for a second and tell me why it's geometric. Why the terms of this series, the things being added, why they follow a geometric sequence pattern. Well, the first term is 1, and the multiplicative value is -2. Because each time I'm multiplying by -2 to get the next term. See how 4 times -2 is -8, -8 times -2 is +16, and so on and so on and so on. And now here's the thing, just from that, I should say, according to this theorem, I have an r that's less than or equal to -1, and so that's going to tell me right away that this series is divergent. You can also hopefully convince yourself of that by thinking about the partial sums of this series. If I add up the first term, I get 1. If I add up the first two terms, I get 1 minus 2, or -1. If I add up the first 3 things, I get a total of 3. If I add up the first 4 things, I get a total of -5. If I add up all these things, I get a total of, like 5 plus 16 is 11. And then if I add the -32 to that, I get -21. And then they're just going to keep getting bigger and bigger in magnitude, in absolute value. I'm going to get some bigger negative numbers and then some bigger positive numbers, and they're just going to keep going like this. Big positive, big negative, big positive, big negative, and back and forth and back and forth. And it's not going to approach anything specific. It's going to diverge. So these are ways to see that it's divergent. And now here's the weird thing. I almost don't even want to write this down and give you bad ideas. But here's the funny thing. If you plug in a and r into the a over 1 minus r formula, you'll get a number, but it just doesn't make sense. I'll get 1 over 1 minus -2, or in other words, 1 over 1 plus 2, or 1/3. Now, how the heck could that possibly be right? It doesn't make sense because the first number I add is 1, and then all the other numbers I add are just even bigger. They're alternating plus, minus, but they're getting bigger in value. How in the world could all of that stuff add up to a small number like a third? That doesn't make any sense. So try to stop yourself from just plugging and chugging with that formula, a over 1 minus r. Don't memorize that as a thing to just use all the time. Stop when you apply it and think about it. Does the answer make sense? And in this case, even if you did this accidentally, you hopefully will recognize, wait a minute, 1/3 doesn't make any sense as the sum of all of these values. And then you'll go back and realize, oh, no, I'm actually in this situation. This is a divergent series instead. Okay, let's modify the original question I asked about the bug and say, what if I change the action so that instead of going forwards all the time, it goes forward 1 inch and then backwards 1/3 of the way? Oops, that's too far. What if I go forward 1 inch and then back 1/3 and then forward 1/9 and then back 1/27 and and I just keep going like that? Looks like a weird eye shape. That was kind of unintentional. But the idea is, what if I add 1 because it's going forward, then I subtract 1/3 because it's going backwards, and then I add 1/9 because it's going forwards, and then I subtract 1/27 because it's going backwards, and so on and so on. So really, I have a geometric series here where a is 1 and r is, in this time, negative 1/3, not positive 1/3. And all of that is going to tell me that this series converges, first of all, because the absolute value of r is smaller than 1. And it's going to add up to the sum of 1 over 1 minus, now careful here because r is negative 1/3. So that's 1 over 1 plus 1/3, or 4/3. And 1 over 4/3 is 3/4. And so what this means is, if I were to measure this step up here of size 1, so if I call that 1 on the number line and that's 0, and then if I were to place a stake right here at 3/4 along the number line, then my bug is going to jump across the stake and then back behind it a little bit, and then ahead of it a little bit, and then behind a little bit, and it's going to keep bouncing back and forth to the left and to the right, but in such a way that it gets, over time, closer and closer and closer to that point that's exactly at 0.75, or 3/4. Why don't you tackle the example at the bottom? Recognize that it's geometric. Tell me whether the series converges or not, and if it does converge, find the sum value. Pause for a second to work on that, and then I'll show you my work. Okay, I hope you recognize that this is geometric, where a, the beginning term, is 2, and r, the multiplicative ratio value, is 2/3, because each time I multiply by 2 in the top and 3 in the bottom, and that's where the 2/3 is coming from. So that tells me right away that this is convergent, the series, because r is smaller than 1 in absolute value, and it tells me that the sum is going to be 2 over 1 minus r, which is 2/3. So in other words, 2 over 1/3, or in fact, 6. That's the sum of this series. And you can play around with this on your calculator or Wolfram Alpha or an Excel spreadsheet. You can maybe set it up. If I keep adding 2 plus 4/3 plus 8/9 plus 16/27, those running totals will become closer and closer and closer to 6. Okay, one final example before I let you go, just to show you a quote-unquote application of this notion of geometric series. You can use this to convert back and forth between rational numbers, fractions, and decimal numbers that have an infinite repeating decimal. So I picked, I hope, a really simple example just to demonstrate this concept. Something that you probably already have seen before in your studies. 0.3333 repeating is the same as the rational number 1/3. So what we're going to do in this example is use geometric series to prove this fact. You've probably already seen this using maybe long division, remainders, or something like that. But here's a way to do it using a geometric series. So by the way, this notation here is just another way of saying that. It's 0 point, and then everything under the bar, which is, by the way, called a vinculum. Nice Latin word that shows up in math, a vinculum. everything under that bar means it repeats over and over and over. So this says threes all the way down the line, not turtles, threes. Let's write this as a geometric series. And here, when I say use the concept of decimal notation, I mean, I'm trusting that you know that this means 0.3 is 3/10. So the first term, the first decimal point here, that's the number 3/10, 0.3. And then if I look at just the next decimal point, that 0.03, because I'm looking at the second decimal point, then another way of saying that is 3 over 100. That's the hundredths place. It's 3 hundredths. Then the next decimal place is the thousandths. So that's another way of saying 3 out of 1,000, or 3 thousandths. That's too many consonants in a row for me to say. NDTHS, yikes. But I could just keep going. Plus 3 out of 10,000, which I'm going to write as 10 to the 4th. And then 300 thousandths, 10 to the 5th, plus, etc., etc. This is a geometric series. You've probably just never thought of it in this way. The A value in this case is 3/10. That's the first term I see in my sum. And what's the R? Each time, to get from one term to the next, I'm multiplying by 10 in the denominator, but the top is always 3, so I'm multiplying by 1/10 every time. And because R is smaller than 1 in absolute value, that means this series converges to the sum, let's see, A is 3/10 over 1 minus R is 1/10. So I get 3/10 over 9/10. And if I have 3 somethings divided by 9 somethings, I have 1 out of 3 of those somethings. In other words, this all simplifies to 1/3. And that's something that you probably knew already about this decimal number.